Okay. So Arianda asked me to give you a few lectures, and I'm going to be here till the end of next month. So I'm going to give one lecture every Friday this time. It should only be 1 hour. And I'm going to call this series Topics in Magnetism. Now, I haven't decided exactly what I'm going to do in the later lectures, but I'm going to begin by doing the same thing I did here a couple of years ago. So the first one or two will be already here 2 years ago. You were the first. But this is a chance for you, right? You're the customers, to tell me what you would like me to talk about. So what I think maybe Nina, is it? Yeah. All right. Okay. So they're going to pass around the sign-up sheet, right? And on the front you just write your email, your name and your email, and on the back you can write some suggestions about some topics in magnetism you would like me to cover in the course of these lectures. So you don't have to speak out now, you just write it down on the back of the paper when it comes around. Yeah? Just what topics you'd like to hear. For example, if you want to hear about crystal fields, or magnetocrystal anisotropy, or magnetic measurements, or if you want me to talk about spin electronics, or tunnel junctions, whatever you like, you stick it down, and you should really don't look at what the other people say, just make up your own mind. And then I'll take a look and see if I can do it. But today it's going to be basic concepts, and in particular I'm going to be talking about units which we should use. So you can read it there. It's a series of 7 lectures on Fridays. And we begin with the basic concepts. We talk about units, and we give values of these quantities for some representative materials. That'll be next time. So what we assume is, you've done basic solid state course, basic electromagnetism course, and basic quantum mechanics course. Supposing that you're well-educated material scientists or physicists or chemists, not engineers, they don't have to know this. Okay, let's go. Of course, I always like to tell you about useful books, and the most useful book is this one. So this is the book which has got it all in, and it's being continually corrected. Every time it's reprinted, there are corrections, and just today I found another mistake which I've corrected. So you can borrow it from the library. You can go to Fishbond and you can buy it for about 100 Sing, or if you have friends in China and you're not too worried about the copyright laws, right? This month there's an English language cheap Chinese reprint which is being produced by Peking University Press, and it costs 107 RMB.
But actually from the NUS website we can download the ebook freely.
Well, I thought that Singapore was a state where the rule of law applied. Obviously doesn't, right?
But this NUS library is paying for it.
They're paying for one ebook, right? And 500 students, right? You know how much I get for one ebook? No, I mean, I get angry. I spent 10 years writing this book, and the way it's being ripped off is terrible.
Yeah, it's one.
Yeah, and NUS is doing it officially, of course. They're paying me as visiting professor, so So this is the book. If you want me to sign a copy, you buy from this point. Okay. So we start off with our basic concepts. Magnetic moments. magnetization and magnetic field. So this doesn't start the way that magnetism courses usually do with paramagnets and diamagnets and all that stuff. We're going to start with the magnet, and we're going to work from there. So here's the magnets. If I had them, I'd bring them. There's a small one, a medium-sized one, 1 centimeter cube, and a big one, 25 millimeters cube. And if you have two of those, you better be careful, because you can hurt yourself. Now, what's associated with each of these magnets is the magnetic moment, or the magnetic dipole moment, because it looks like, the magnetic field looks like that in the dielectric dipole. And this magnetic moment which is little m is a quantity of the magnet, is proportional to the magnetization, which is a quantity of the material, times the volume. So that's simple. And if we suppose they're made of neodymium iron boron, which most of these magnets are, nowadays they're either made of neodymium iron boron or sodium ferrite. For neodymium iron boron, the magnetization is about 1.1 megamps per liter. If they're made of ferrite, the moment is about 0.4 megamps per liter. So let's say 1 megamp per liter. And let's look at that 1 centimeter cube magnet in the middle. It's 10 to the minus 6 cubic meters. 1 centimeter to the minus 2. So the magnetic moment of that magnet is 1 amp-meter squared. So now you understand the unit, right? You take one cubic centimeter of some strong ferromagnet, and the moment is 1 amp-meter squared. So it's easy to get hold of. Right? If you stick one of those magnets on the fridge at home, it's probably about maybe half amp-meter squared or something like that. So what are the moments that they are? Right? I mean, I took one, so 1 megamp per meter. This is 1 amp-meter squared. That's 17. And that's now, the next thing you have to realize is that magnetic moment is a vector. Right? So if I have a couple of these, and this is how you indicate the direction of magnetization of a magnet. It's done with an arrow. When you were at primary school, they had red horseshoes and they had M's and S's written on them. We don't do that. It doesn't actually make good sense because these quote poles are a fiction, a mathematical fiction to represent the magnetization. So you think that m, little m or big M is a vector, and the direction of the vector is shown by an arrow. So usually, conventionally, in books where you show a permanent magnet in a magnetic circuit, it's not shaded, it's usually white, and it's just got an arrow. And that shows the direction of magnetization. Now, of course, everyone knows, and it's been known for 2,000 years, that the magnets will attract or repel according to their orientation. Actually, the ancient Greeks didn't know that they would repel. They just didn't notice. Ancient Chinese were a bit smarter. Ancient Indians, they were doing nothing. Okay, so let's see. So when you put them like that, do they attract or repel? Who thinks they attract? We're voting. Right? This is no way to decide stance, right? Who thinks these two magnets attract? Who thinks they repel? Okay, of course they repel, yeah? So voting works. So if we put them like this, do they attract or repel? No. But if we put them like that, they repel, right? And they repel pretty fiercely, right? Okay. And if you just throw them together like dice, they'll end up sticking together with the moment along long axis. So there's the summary about what happens with these magnets. They're weakly repelled like that. They're strongly repelled like this. They're strongly attracted like that, and weakly attracted like this. And of course, okay, that's a picture of Niedermeyer boron. We'll come back to it later. But the point is that these magnets, the axis of the magnet is always, the axis of magnetization is always the axis of the crystal structure. You can't make permanent magnets from cubic materials. They have to be made from uniaxial materials. So that means that they're almost always hexagonal or tetragonal. They could be orthorhombic, they could be monoclinic, but almost all of the useful materials belong to those two classes, and Niedermeyer and boron is a tetragonal compound. So that's why I'm showing this structure. So what do the units mean? Well, if the magnetization is in amps per meter, and the magnetic moment is in amps meter squared, what does it mean? I mean, those are amps, right? You know what amps are, right? Because of current, right? And you know what a meter is. So what's the deal? I mean, how do we get amps meters squared or amps per meter relative to these basic magnetic quantities? Well, the person who sorted it out was Ampere. He just before Ørsted made the discovery, Ampere sorted it out, and the point is that if we have a current loop, if we have a loop of current carrying current I, and the area is A square meters, then the magnetic, that current loop is equivalent to a magnet, behaves just like a magnet. You know, you put them with the moments in opposite directions like this, like that, and all that stuff. And the magnetic moment is IA. I in amps, A in meters squared. So there's the relation between magnetism and electricity. It's straightforward. But this is a very interesting idea, and it's got some very, very surprising consequences. For a long time, people couldn't believe it. Now, if we have n terms, of course, we have to multiply by n if we have n terms of a coil. And the other thing that you need to know if you're ever going to have any confidence in magnetism, you need to be able to work out the directions. Right? And to work out that directions, you'd have been taught it when you did your elementary E&M in first year university or whatever it was. But everyone has got their own way of doing it. You just need to have one that works. So some people do things like this, but I do this because I like corkscrews. I like to think that, taking out the cork from the bottle. And this right-hand corkscrew will give you everything you need. It will tell you the direction of the vector product. It will tell you the direction of the moment if you know which way the current is going around the loop. So the current is going around the loop just like that. Check your method and see that you get m in the right direction. Right? Here's my method, right hand. The current is going around this way, so the magnetic moment is like that. Okay? You just need something you're completely confident in that works. Now, I told you that that little magnet cube, 1 cc, has got a moment of 1 amp meter squared. But what would the coil look like that's got the same magnetic moment? Well, this area here is 10 to the minus 4 meters squared. So we would have to have 10,000 terms carrying 1 amp, which you could hardly imagine winding in that space. Or you could have 1 turn, if you wanted, carrying 10,000 amps. Now, This is why people had a little bit of trouble with Ampere's idea, relating the current loop to the magnet, because where is this surface current of 10,000 amps per centimeter? Where's it coming from? What is it? And in fact, this was 100 years ago or so. This was one of the big puzzles that magnetism presented, but people didn't quite understand what a paradox it was. And it wasn't until we understood both quantum mechanics and relativity we could explain it. Right? And particularly here, if I take my magnet, my piece like that, it's as if there's this current, this huge current running around the outside, and this current is related to the, it's largely related to the spin moments of the electrons, and you can regard them, certainly the orbital moments, you can regard as current loops, which are quantized. So even though you have got this effective huge current, it doesn't do any harm, it doesn't melt the thing, because it's due to electrons in stationary states. And the key to understanding magnetism and quantum mechanics is that it's just related to angular momentum of electrons. But let me go on. Now, another point to see here is that we could never design simply copper circuits that could produce anything like this density of magnetization. I say that the permanent magnets will win over electromagnets, or coils, certainly they'll win over coils at small volumes. If you're trying to produce a huge field, you might actually take a bitter solenoid and you might pass a huge current through it, but you can create large fields in relatively small volumes with an industrial size operation, but on a big scale. If you want to make magnetic fields on a small scale, if you're interested in, say, micromechanics or stuff like that, you have to use permanent magnets, or alternatively use ferromagnetic material, which are temporary magnets, but it's the same. Now, that was the famous moment in history when Ørsted, who was a Danish professor who liked to do demonstration lectures, finally stumbled on the connection between electricity and magnets. And that was just 6 weeks before Ampere did that experiment, because the news traveled very, very quickly from Denmark, where at last they discovered this connection between currents in the wires and magnetism, which people had been looking for generations. And this picture actually illustrates what the paradox was, because this professor used to give his demonstration lectures, and he would connect a copper wire to an electrified cell, right? A voltaic pile, and he would electrify the wire. Of course, nothing happened. And also, people couldn't imagine that if there was a field associated with the electric current, it seemed to be obvious it would have to be in the same direction as the wire. Of course, it was wrong. We know that the field is perpendicular to the wire. In fact, the right hand, the good right hand, this is the direction of the current. Now, the thumb tells you the direction of the field. It's loops around the wire. And that's what Ørsted discovered in 1820, that's why he's famous. And Ampere's law says that if you integrate the magnetic field, which I haven't defined, around any loop containing a current, the integral of HDL is equal to the current threaded through. So you can see that if HDL is amps, then H is in amps per meter. So notice H is in the same units as M. And this tells you that h is I over 2 pi r, where r is the distance from the wire. Now, if I is 1 amp, and we're looking at the field, so this is now to give you a feeling for the H field, we're looking 1 millimeter away from this wire, which has got an amp flowing through it, then H is 159 amps per meter. That's just about twice the Earth's magnetic field. So, one wire produced a pretty weak field, even if you're very close to it. The Earth's field is about 50 amps. And even if you make a solenoid with many, many turns, with n turns per meter, then the field inside is Ni, that's the current, so H is in amps per meter, is the number of turns per meter times the current. Okay, now, I've got two things I want to say on this slide. The first one is that, of course, the field due to a magnetic moment is this strange shape. It's actually, the Earth has got a dipole moment, and the Earth's field looks something like this too. It's just like the field of an electric dipole. It's twice as large on the axis at a certain distance as it is in the equatorial plane, and the magnetic field of the dipole we can write in about 3 different ways, but here I'm writing it in terms of 2 vectors, one along r, which is this one, that's the radius vector, sorry. R is in that direction, unit vector r is in that direction, and unit vector theta is in the perpendicular direction. So it goes as magnetic moment, it falls off as 1 over r cubed, and this just says that it's the 2 on the cos and the minus 1 on the sine is just repeating what I just said about its anisotropy. So the important thing is the field in amps per meter due to the magnet, a moment in amps per meter squared, just looking at the units, it goes as 1 over r cubed. And that falls off, that's quite a quick fall off. But it's extremely adventitious because what it means is, and in a later lecture I'll talk about this, because this is what has brought us into the information age, big data, and it's changing all our lives. Magnetism has changed the world 3 times. 3 revolutions which have been based on magnetism. And the last one is the information revolution and the era of big data, which is going to reap terrible changes. And it all depends on this 1 over r cubed. Because if I take another magnet, which is, say, 1/10 the size, right? Then the magnetic moment will be reduced by a factor of 1,000. But if I look at the same position, right, and I scale everything down by a factor of 10, then because of the 1 over r cubed, the field will go up by 1,000. So that shows you that the magnetic field is scale independent. We can draw a magnetic circuit on a piece of 3-dimensional elastic, and we can pull it out or squeeze it in, and we'll get it. We won't change anything. And this is what has permitted, and of course scaling is what you need if you're going to invest billions in a semiconductor fab, because you don't do it for 1 generation, for 1 node. You've got to make that investment so that you can scale whatever the technology is. You can reduce the dimensions by a factor of root 2 and a factor of root 2 and a factor of root 2 again, so that you can keep on the Moore's law curve. And magnetism and magnetic recording is perfectly adapted in this sense. And I'll show you the extraordinary progress that possible by this later. You just need to realize that they're scale independent, as this simple example works out. There's the little magnet, and that A, the field is going to be exactly the same here and here, if we use the same material. And of course, the other point is the Earth. The Earth is, the first approximation, the leading term, if you do a spherical harmonic analysis of the Earth's field, which was done first time by Gauss, who invented spherical harmonic analysis for just that problem, to analyze the Earth's field. You know that the axis of the geocentric, the best fitting geocentric dipole, is off by about 15 degrees or 10 degrees, and this magnetic axis is moving with time. You can work out actually what they, if you know that the field here is 50 amps per meter, and you know that the radius of the Earth is 6,000 kilometers, you can figure out what the magnetic moment of the Earth is, and get the average magnetization. I'm not setting problems. Okay, so now we've introduced magnetic moment, magnetization, we've seen the relation with current, and one magnetic field, which is the one produced by current. Now we'll come back to our ferromagnetic material, to our needling iron ore. And if we now measure the magnetization as a function of field, and this is not something we can do to come to because they're both in the same units, so there's no confusion. This curve here, this hysteresis loop, is it's m as a function of h when there's no constant. This is the relation between m and h. If I was to take that magnet and I was to measure the magnetization, I would measure my 1.1 megamp per meter, not actually here, as you might think, because we're applying no field, but the magnet is sitting at a point there because it is generating a field, it's demagnetizing a field on itself. I'll come back to that later. But the main point about this loop I want to get across at the moment is that if we then apply our reverse field, H, in the opposite direction to the magnetization, then at some point the magnetization will collapse. And if I carry on increasing the H field in the opposite direction, I'll eventually come back to the saturation, the 1.1 megamp per meter, this way. And if I then bring down the field back to 0, I'll actually be there, and then I reverse it, I'll trace this loop. And every time you go run this loop, you generate the cost energy, and the energy required to circulate around the loop once is the area of the loop times mu naught. I'll do that in a second. This shows the little cartoons show what happens to the domains as we go around the loop. That will be something I'll talk about later. But the permanent magnets have got a big loop, so they don't demagnetize themselves. And the temporary magnets, like iron, have got a very narrow loop. So iron, if you take a paper clip, it is magnetized, but there are many domains in all different directions, so there's no net magnetic moment for that bit of iron. So you can't pick up one paper clip with another. You can only do it if you magnetize the first paper clip in the permanent magnetism. So that's a soft magnet. And the slope there, it's supposed to have very little susceptibility, very little hysteresis, and the slope is the initial susceptibility. So let me just define the quantities around the loop again. This one is the saturation magnetization, or the spontaneous, well, yeah, it's the spontaneous magnetization, which is the magnetization within a domain, MS. Then it comes down to zero at a field known as the coercive field or coercivity. And in zero applied field, the magnetization is usually a bit less, and that's called the limits. And if you start off with it completely unmagnetized, if you just put it from above the Curie temperature, then you follow this initial curve, but you only follow it once. So that's why it's called the virgin curve. And the slope there is the initial susceptibility. So here I'm looking at the two most common, or two or three common ferromagnets: iron, nickel, the other ferromagnet is cobalt, and permalloy, which is a very useful alloy. Iron 20, nickel 80. And the magnetization, the spontaneous magnetization, where the magnetization saturates, is 1.7 megamps per meter for iron. It's about 0.5 megamps per meter for nickel, and permalloy is 0.3, 0.8. And of course, as you know, if you heat it too much, the spontaneous magnetization collapses, and that's the Curie temperature. And the Curie temperature for iron is 700 Kelvin, and almost 800 for nickel, it's about 350, permalloy about 600. But, so if a ferromagnet is to be useful at room temperature, it has to have a much higher Curie temperature. Okay, well, now we've got the idea of magnetism and magnetic materials. It's in the interest of truth in advertising, there are not many elements in the periodic table that are ferromagnetic. There are 3 in Singapore and 4 in Ireland. 3 you've got in Singapore are iron, cobalt, and nickel. And the extra one we have in Ireland is gadolinium, because the Curie temperature of gadolinium is 296 Kelvin, and most days in Ireland it's less than 23 degrees centigrade. Right? But in Singapore, it's always 29 or more, right? And gadolinium doesn't stand a chance. Now, besides that, I don't know if I have it here, but there are other rare earth elements that have got a low Curie temperature. Another interesting one is dysprosium. It's got a Curie temperature just above liquid nitrogen. So if you take a piece of dysprosium and put it in liquid nitrogen, it becomes actually very strong nitrogen. But that's not usually the case. Most other elements are either paramagnetic or diamagnetic. They've got this rather uninteresting response to a magnetic field. Either you induce a weak moment in the direction of the field, or the material tries to keep the field out, and you induce a weak moment in the opposite direction of the field. Now, M over H is the susceptibility. Susceptibility, of course, has got no units, because M and H are both in amps per meter. So this is a useful number. It's not the one you often measure, because you don't usually measure the volume of the sample unless it's a thin film. Usually you measure the mass, so you have to know the density. Now, how big is the susceptibility? Well, it's some at room temperature for many materials. It's some number like 10 to the minus 6. So it's 1 part. It's plus or minus. The strongest diamagnet, well, of course, the strongest diamagnet is a supermagnet, for which susceptibility is -1. The B field is excluded. But then, next best is graphite. And the susceptibility of graphite is terribly anisotropic, because you've got a relatively large diamagnetism if you measure perpendicular to the graphene sheets, and one that's about 100 times smaller if you measure in the graphene sheets. And in fact, it's possible to, as I'm sure you've seen, to levitate a magnet, a ferromagnet, a permanent magnet, like a superconductor, a large superconductor, for reasons that I explain perhaps. You can also do the same thing without any liquid helium or liquid nitrogen. You can take a piece of graphite, HOPG, and it will float just a little bit above that magnet I showed you at the beginning. Or better, you take 4 of them, just put them together. And there's a stable point in the middle where the graphite is a bit strong, relatively strong diamond. So as I say, chi is, well, the range 10 to the minus 4 to 10 to the minus 6. And there's a whole zoo of magnetic order which I won't get into yet. That's a ferromagnet where what do these things represent? These circles represent the atomic magnetic moments. So each of these circles is supposed to be an atom, and in a ferromagnet, the individual moments possessed by the atoms are aligned by strong Coulomb interactions in this exchange. But there are other possibilities. They may tend to couple opposite to their neighbors, in which case we can get an antiferromagnet, which doesn't have a net magnetization, though it's magnetically ordered. Or, like barium ferrite, we may have two different sublattices with different moments. So those are the magnetically ordered states, some of them below the Curie temperature, and above the Curie temperature, they will all become paramagnetic. That means that the individual atomic moments are fluctuating around them, and you just you'll introduce a small magnetization against the thermal disorder effectively. So here at last is our magnetic periodic table. If you buy the Chinese reprint, right, you get a free magnetic periodic table, which you can stick on your fridge, right? And even some of it is written in Chinese. But not the names of the elements, because nobody in China actually knows the Chinese names of the elements, or only literati. So there they are. So here are the 4 ferromagnets, the blue ones. Here are some other elements which are ferromagnetic at low temperatures, like terbium and dysprosium, holmium and erbium, these rare earths. The green ones are the antiferromagnets, and chromium is antiferromagnetic at low temperature, and many other rare earths are. And if it's got a green and a blue, it means that there's a phase transition that's ferromagnetic below some temperature, and then it turns antiferromagnetic, and then you come to it, or the other way around. I notice that this magnetism is completely concentrated in the 3D series, this magnetic order of the elements, or the 4F series, and you don't find it anywhere else except oxygen. So oxygen. Solid oxygen, what you can't see here, it tells you what the ordering temperature is, it's just 35 Kelvin. Solid oxygen is a molecular solid, and so it's formed of O2 molecules. And the interesting thing about the O2 molecule is normally you take a couple of atoms with a spin, and like H2, like hydrogen, they form this bonding state. Right? But oxygen with S equals 0, sigma equals 0. But oxygen doesn't. it forms a state with sigma equal to 1 if you take a couple of oxygen atoms and put them together. So the oxygen molecule has got a magnetic moment. And these magnetic moments in the oxygen molecule order antiferromagnetically in solid oxygen below about 30 Kelvin. All right, now we have to come back to this question of magnetic fields, and we have to distinguish a little bit more carefully what this H field is. I say you apply a field H. But you can apply a field H. Let's see. Let's go. Okay. There's lots of ways you can create magnetic fields. You can create it with Helmholtz coils, or with solenoids, or a superconducting solenoid where we've got many turns, or a permanent magnet, or an electromagnet. And the Earth is a magnet that creates a field. And the biggest field in the universe is 7 sorts of neutron stars. So I'm now back to the idea of let's think of a thin film of iron. And I'm going to apply the magnetic field H, which I know what it is because I've actually got some sort of Hall probe in there to measure what the field is at the iron film. And if I measure the magnetization, which is the average over the film, with the field in the plane, I find that it saturates almost immediately. And if I now apply the field in the other direction, perpendicular to the plane, you find that it actually increases uniformly until the applied field is equal to the magnetization of iron. So that means that in order to saturate this iron film, you've got to apply a field of 1.7 megaamps per meter. That's a big field. You can get that. You can get that just about with an electron. And the reason is that what the field the iron sees is not the field you apply. It's the field you apply plus a field that it creates itself. And this field it creates itself is the demagnetizing field, and it's always in the opposite direction to the magnetization. That's why it's called demagnetizing. A superconductor is the other way around. You apply a field to a superconductor actually amplifies the field, but the ferromagnet decreases it. So that's the point. And how big the demagnetizing field is depends on the shape of the sample. Now, the example I gave you, that's the worst case. You never get a demagnetizing field that exceeds the magnetization. You only get it in that case. Any other shape will give you a demagnetizing field that's less than the magnetization. And so there's a demagnetizing factor. And this is the easy way is just to think this is a number, and it's really a tensor, but let's just take it as a number. And so the demagnetizing field created by the moment, by the magnetizing material, is minus this number, which is between 0 and 1, times the magnetization. Now, more generally, as I say, this is a tensor relation. It's Hi is equal to minus Mij Mj. And there's a result which you can show that if you take the 3 principal axes of the demagnetizing tensor, which in the case of the thin film, there obviously going to be 2 directions in the plane and 1 direction perpendicular, and you take the sum of nx, x plus n plus n, x, it must be equal to 1. The trace of that tensor is 1. And so if the demagnetizing factor is if nzz is 1, then it follows that nxx and nyy are 0. So there's no demagnetizing field in the plane. Okay. So the other point is that the internal field is always less than the applied field because of this demagnetizing effect.
Okay.
Yep.
What is the origin of demagnetizing field?
That's what I'm just come to in a minute. But let me just go on a little bit, and let me show you how at least you can calculate stuff for simple shapes. You can find what this n is. For a sphere, for example, it has to be 1/3, because x, y, and z are the same. So nxx plus n or y plus nz equals 1, and any one of them is a third. If we take a long cylinder, right? The demagnetizing factor is 0 along the axis. If it's magnetized along the axis, and if it's magnetized perpendicular to the axis, it must be half. There are some shapes for which n is 0. One is a ring like this, well, one is a thin film in the plane, and the other one is a very, very long rod. And we'll see when I explain what the origin of that field is. And that's the case I already talked about, where n is equal to 1. Now, this then tells you why, or it tells you a lot about the history of magnetism. Because this demagnetizing field, for the best part of all the history of magnetism, except the last 70 years, right, people could not control they could not counter the effect of the demagnetizing field. And if you take a soft material, because what's important is we need a material coercivity to make a good magnet. For centuries, people had materials with very, very weak coercivity. And the only way that you could make a magnet was to make it of such a shape that the demagnetizing field was less than the coercive field. And this is what was described nicely by J.M.D. about 1,000 years ago in China. This is a steel needle, and it's magnetized along this long axis. Then, about 700 years later, Daniel Bernoulli, who was actually a mathematician, and he gets the credit, but in fact the discovery was made by his blacksmith, had the clever idea of taking this long bar and just bending it into a horseshoe, which is topologically the same, and more or less just as good so far as the demagnetizing effect is concerned. And so it was possible to make horseshoe magnets out of iron. And these things, you can still see them sometimes in science books that are used in primary schools. They've been completely obsolete for 60 years. But it's such a powerful icon of magnetism. If you ask someone what's a magnet, they'll show you something like this. That's not what they're like. If you reverse engineer any bit of electronics in your mobile phone or your portable stereo or whatever you want, take out the magnets. They don't look like that. They look like this. Because since 1950, there have been materials with enough coercivity that were able to make the magnets any shape we like. And the most efficient shape, as you can show easily in this two-line argument, the most efficient shape for a magnet is a shape which has got a demagnetizing factor of half, 0.5. And if you make it a cylinder, it's going to look something like that. So that's what the icon of permanent magnet of magnetism should be, but it's not very good for PR. Doesn't say anything, it's just exactly true. So that was the shape barrier, and let me just explain that a little bit more. Here's the hysteresis loop of our material. Now, the demagnetizing field is minus n times n. So, if the demagnetizing field is less than the coercivity, then I'm afraid this magnet has killed itself. There's no stable magnetization. It's only going to work if the demagnetizing field is less than the coercivity, and then it's going to sit at this working point. Right? And the field, now H is now the internal field, the field the magnet sees. You can see it's in the opposite direction to M, it's negative, and the magnet sits at this working point in the second part. So, for thousands of years, the coercivity was limited to hard steel. So the only way around it, the only way to make a magnet was to choose something which has got a very, very small demagnetizing power. That means either a bar or a needle or a horseshoe. As I say, that's now no longer the case, and all the books have been rewritten. Okay, now, there's one other field which we must deal with today before we stop, and that's the most fundamental one. So this is the famous B field, which is the magnetic flux density, and which you see, for example, in Maxwell's equations. And one of Maxwell's famous equations is that the divergence of B equals 0. And when you're taught electromagnetism, this is the first field that you're introduced to. Right? There's a good reason for that, because this expression dB equals 0, that expresses a fundamental truth, which is that there are no magnetic poles. The only sources of field are essentially currents and magnets. And the sort of north and south poles, they're a mathematical fiction. They're a way to represent the field. Sometimes nowadays we call it magnetic charge. And maybe somewhere in the universe there is one magnetic monopole. That's what Dirac said. We only need one in order to quantize charge. Just need one somewhere in the universe. And if you talk to string theorists, which is a sort of a fantasy field where I'm a physicist, they of course are completely conversant with the existence of magnetic monopoles. But there have been careful experiments done, mainly about 20 years ago, to try to capture one, to try to see a monopole going through a coil attached to a spindle, and there was a very, very low density to show that essentially none of these things were flying around. So there's Maxwell's equations. It says dB equals 0, and what it means is that the lines of this field don't start or stop anywhere. It's not like electric field where we've got electric charge, right? Electric field starts on the lines of E start on the positive charge and they go around to the negative charge and they stop. Lines of B are always continuous loops. They don't stop or start anywhere. The lines of H, however, and this is where the idea of magnetic poles actually comes in. The lines of H are like the lines of E, and I'll show you that in a moment. But this is the important thing, that the lines of B always form complete loops. You can write this either this way, or you can write it as an integral, and it says that over any closed surface, we integrate B over any closed surface. That means B dot dA, but that's the little vector area, and that must be 0. So whatever lines are going into any closed surface must come out. B is also known as the flux density, it's another word for it. And it has units. It has its own units, and the units of the unit of B is the Tesla. Now, in free space, there's not much difference between B and H. The lines of B, the lines of H look exactly the same. They're indistinguishable, except they're different quantities, they're different physical quantities, they're measured in different units, and so there's a proportionality between them, but the constant of proportionality between B and H is a constant with units. And it's known as the permeability of free space. So in free space, B is equal to mu naught H, or mu naught, is exactly 4 pi times 10 to the minus 7 Tesla divided by amps per meter. That's a number which has been fixed by convention in the unit system, which is the same unit system that your Keithley uses. Your Keithley measures in volts, amps, and ohms, right? And it's pretty useful if you're going to do any sort of experimental science to use the same units that your measuring instruments give you the answers in when you discuss the quantities. Now, so, I mean, I haven't explained, well, I've only hinted at what the real difference between B and H is, but let me stick with mu naught. Whenever the H field interacts with anything, so suppose the magnetic field interacts with the magnetic field, or sound, then whenever there's that interaction, we generate a force or an energy or an EMF or whatever it is, then we have to bring in mu naught. For example, the energy of magnetic moment M in a field H is minus, is the minus not last, mu naught M naught H. The torque on a magnetic moment M in the field H is mu naught M cross H. So any energy expression, right, is always a product of something with the dimensions of B, i.e. mu naught H, and the dimensions of M. So little m if it's simply an energy, big M if it's an energy per unit volume. So that's the energy of a dipole in the field. The dimensions of mu naught, you can figure them out. Now, you can express the Tesla, which is just a special name, in terms of the basic units. That's something which you can do in your spare time, or you can look at the last slide. Here are values of, now, here I've shown the various field sources. I've shown actually the D field they produce. I mean, outside in free space, it's just proportional to H. We just multiply by, to get from B to H, we multiply by 1 over mu naught, and that's almost 800,000. It's not exactly 800,000, it's 1 over 4 pi times 7. So, for example, you're used to these units of B when you talk about, say, a 10 Tesla superconducting magnet, or the PBMS, or an electromagnet producing 1 or 2 Tesla, or the Helmholtz coil producing 10 millitesla, or the Earth field is about microtesla. You just convert from D to H in free space by multiplying by mu naught. Now, so here at last is a bit more explanation about the relation between B, H, and M, and why we have a demagnetizing field. So the general relation between B, H, and M in a magnetic material is B is equal to mu naught H plus M, mu naught H plus M. if m is 0, if we're in free space, B is mu naught h. We've seen that, but this is what's generally the case. So let's consider a bar magnet. There it is, it's got a uniform magnetization M. And this creates a B field, which is like the field of a dipole outside, but inside the lines continue. We've got this continuous loops. But the H field is different. Outside it's the same as B, inside it's in the opposite direction. So we call the H field, due to the magnet, we call it the stray field outside, and inside it's called the demagnetizing field. And we can rewrite H as, in fact, this is the right way to define H. We take B divided by mu naught minus M. These are boundary conditions. Gauss's law will tell you that the perpendicular component of B is continuous at the interface, and the parallel component of H is continuous at the interface. And if you look at these, there's the perpendicular component of B being continuous, and there's the parallel component of H being continuous. Now, let me see how many more of these slides I've got. Okay, we're near the end. We've got about another 10 minutes. Is it okay? Or should I put you aside? Okay. Now, if we go back to our lithium-ion boron, what I said was that it had a tetragonal structure, and there was a strong tendency for the magnetization to lie along the tetragonal axis. And what that means is that if we were to try to magnetize it in the perpendicular direction, perpendicular to the tetragonal axis, we would only slowly be able to rotate the magnetization into the direction of the field. And in fact, we can represent this tendency for the magnetization to be fixed to some directions in space, which we call anisotropy. We can write it as an energy, or we can think of it as a fictitious field, called the anisotropy field. For lithium-ion boron, the anisotropy field is about 6 Tesla. So we'd have to apply a pretty huge perpendicular field to be able to move the magnetization of that magnet out of its easy direction. So the way that we can represent that, at least the leading term, is we can say that the energy deviates, or it increases as the magnetization deviates from the easy axis, and we can write that as K sine squared theta. K is the energy volume, and it has to be sine squared because magnetism is time reversal invariant. If we just switch the direction, if we switch the direction of the currents so they go around the other way, we invert all of the moments and we've got the same energy. So this is the general expression. We can write shape anisotropy, which I've already given you enough to be able to figure out what that means. It depends on the demagnetizing factor n, like this. So we can give an expression for k in terms of the magnetization and n for shape anisotropy. And shape anisotropy is actually never enough to create a true permanent magnet. That's why they had to use those strange shapes. This is just another point that sometimes people, instead of talking about magnetization, they talk about polarization, which is just mu naught m. So the polarization of iron is 2.15 Tesla, its magnetization is 1.7 Tesla. And the anisotropy of whatever origin could be represented by this fictitious field, which is 2k1 over mu naught m. Okay. I've said that. And this we've already dealt with. We've seen the magnet sits at its working point, and I haven't introduced energy products, so I won't talk about it. This, actually, the energy, now here, incidentally, notice this is a different hysteresis loop. what I'm plotting here is the polarization in Tesla, right? Or B in Tesla as a function of H. So this one doesn't saturate flat, it saturates with a slope mu naught, because B is equal to mu naught H. And it doesn't change. Here are some expressions that you know. These are all expressions involving B.
So it's criteria for finding the working point?
Sorry?
What is the criteria for finding?
Oh, okay. Well, you see, if you want to design a good magnet, right, the figure of merit is it wants to sit at a working point where this product BH is as big as possible. This is the so-called BH max criterion. And BH is an energy per unit volume, like I said, to multiply summing with dimensions of B with summing with dimensions of N or H. You get an energy per unit volume. So you want the material to have a loop, a hysteresis loop, which allows you to make BH as big as possible. And if you have a square loop, you achieve that with N equals a half. These are the expressions, some expressions that you find in textbooks which relate force or energy, torque to the B field, force on a charge, force on a wire, Faraday's law of electromagnetic induction, that's the EMF, energy of a moment, force on a moment, torque on a moment. Now, my last comment today is about units, and I've been at pains to make the point that we're using SI units, and these are practical units. These are the ones that we read on the key or the oscilloscope. And there are some reasons that you really ought to use these. But apart from the fact it's what you learned when you did your elementary physics and engineering courses. And the first important unit is that they relate to what you're familiar with. The second point is you can check the dimensions of any expression. You can see it, basically you can see if you made a mistake just by checking the dimensions. And you cannot do that with the whole system of CGS units, because mu naught in CGS units is 1, but it's got dimensions. It's not the number 1, it's a constant, it's a dimensional constant equal to 1. And so you don't ever bother writing it in an expression, and you can never tell if you missed it out. Whereas in this case, if you missed out mu naught out of an expression, first of all you can check the dimensions, and then you can do a reality check, because the answer will be about 1 million times wrong if you left out mu naught, because mu naught is almost immutable. However, having said that, CGS units still exist. They're very popular in America and also in Japan. And there you have something called an EMU, which is not actually a well-defined unit. It could be an EMU of magnetic moment or susceptibility. It's all a bit confusing, but you can look at that. What people know are Gauss, right? And there's a relation between B in Gauss and B in Tesla. Conversion factor is 10,000. You need to be careful, because the susceptibility, dimensional susceptibility, is not the same in the two systems. There's a dimension, and dimension is factor 4 pi. So here I'll circulate this, and this is a useful table. These 4 tables, they give you the dimensions of all the common quantities that you use in physics. So we start off with mechanical quantities, where the dimensions of area, for example, are. So these are the basic quantities: mass, length, time, current, and temperature. Those are the 5 basic quantities that we use. So energy, for example, is mv squared. I said, okay, that's right, mv squared. Mass and velocity is length over time, so 1, 2, minus 2, and so on. These are the electrical units. Notice these are all nice integers, right? Which, if you try this in the other system, you get some very strange things like numbers like 4/3 and so on. So these are the dimensions of resistance, for example, in terms of mass, length, and time, and current. 1, 2, minus 3, minus 2, and so on. These are the magnetic dimensions. H, wherever it is H, in amps per meter. B, the units, the dimensions of B, mass, no length, T to the minus 2 per meter, so it's like kilograms per second squared per amp. Mu naught, there are its dimensions and so on. And there are thermals. And so, at the end of this are a few little examples showing how you can check lots of expressions. When you write down an equation, the dimensions of each, and the terms being added, the dimensions of each term that you're adding must be the same. So if we look at, for example, B equals mu naught H plus M somewhere here, you can check that the dimensions of B are the same as mu naught times H. And when you multiply two quantities, you simply add the dimensions, divide them and subtract. This Ohm's law equals IR, check it out, or Faraday's law. So I would commend you to get your head around this. Okay? And never, ever write a paper with a figure where the horizontal axis is H Tesla. So if you get a negative referee, just pay what it is. Okay?
We used to do that.
I know, yes. But you probably now you know better.
Yeah.
H can be in amps per meter, right? If you use the SI system, H can be in Ørsted if you use the CTS system, but H is never. At least not in any of these conventional systems. I mean, you can make up unit systems to your heart's content, but these are the two that are used. Yeah.
I have a question. Like H has a magnetic field, right? F has a magnetic field.
Yeah.
Like all of the planets have their own magnetic field. Then
Most of them do, yes.
yeah. So what is their impact on F? Let's say we have mentioned 50 amp per meter.
Yeah.
That's the F magnetic the maximum we said.
Yeah.
But what about the other planets? Because we are surrounded by so many planets.
Of course we are. Well, we're surrounded by a few planets, but what you must understand is that the field falls off as one of our cubes. Right?
Yes, a micro Tesla.
So if at the surface of the Earth, which has got a radius of 6,000 kilometers, right, you measure 50 amps per meter or 50 microtesla, whichever it was. Even when you get to the sun, even when you get to the moon, let's take the moon. Okay, the moon is 240,000 kilometers away. Right? So that's 40,000 times. 240,000. Yeah, it's a factor of 40 times the radius. 40 cubed is 1, 2, 3, 4. Right? It's 10 to the minus 4. So the Earth field, even at the moon, right, is about 10 milliamps per meter. Those fields fall off very, very fast. Now, what you do find, however, in space, in deep space, you find a weak trapped magnetic field. Okay? And that's something left over from certainly from the condensation of this solar system and the creation of the stars here. And And that's because of the magnetohydrodynamic conditions when that was going on mean that the field is not independent of the medium it's sitting in. It's got trapped. But that weak interstellar field is not produced by magnets anyway. I mean, the Earth has got circulating currents in the liquid core, right? Some very complicated motions which are partly chaotic, which create the field. And it fluctuates in time because the hydrodynamics in the Earth's core are very complicated. But you can't, and the sun, well, the Earth's magnetic field will reverse erratically about every 100,000 or a million years, something like that. But it's essentially a random process. The sun has a magnetic field, it reverses every 11 years. So there's an 11-year cycle corresponding to a sunspot cycle. And the field at the surface of the sun is maybe 50 or 100 times that of the Earth. But these internally generated fields have essentially no influence on other cellular bodies.
So what is the origin of the magnetization field?
What? Well, the origin of the demagnetizing field is well, there are different ways you can think about it. You can think about that. You can think about it in terms of if you wanted to set it up from scratch, if you wanted to take a piece of material and magnetize it and create those effective currents, you would have a sort of lenses law effect, which would tend to prevent you from doing it. And in a sense, that's what the demagnetizing
So at the atomic scale,
yeah.
that's also happened.
But a really good way to think about the demagnetizing field, and this I didn't say, but it's a good way to think about it. If you look at it here, right, this H field could be produced by, if it was electric, it would be produced by a layer of positive charge on the top and negative charge at the bottom. That's where the dipole idea comes from. Now, you can formally think of the H field as being produced by magnetic charge. And the magnetic charge is formally in a uniformly magnetized body, the charge density on a surface is m dotted into the unit vector normal to the surface. So it's as if we have a magnetic charge density of m on this surface plus m here minus m there. And those things are the north and south poles. People used to talk about. If the magnetization is non-uniform, then you've got a volume charge, which is the divergence of it. And even though I've been careful not to make much use of it, for purposes of calculation, this is very convenient. It's actually very convenient if you want to calculate the H field in any particular circumstance, and particularly when you've got uniformly magnetized blocks of material, just use this convention. You can cover the surfaces with magnetic charge, and then you've only got to do surface integrals in order to get the field and the expression for the field. Due to a charge, it goes to 1/r squared, whereas a dipole goes to 1/r cubed. So that's not a fundamental answer to the question, what's the origin of the demagnetizing field? It's an answer to the question as to how you like to calculate it. Easily. I mean, there are three ways you can do the calculation. The point charge, the surface charge model is the easiest. You can also sum the dipole. You know what the field should be. The dipole is, you can integrate that over the whole volume, or you can take the equivalent surface currents. Those are three different ways to calculate magnetic fields, and they all must be equivalent. And you do whichever is easiest.
The material space can interact as a ferromagnetic or anti-ferromagnetic. So what makes them interact as a ferromagnetic? How?
Okay, well, that we come to later, but the important thing to understand is this has nothing to do with anything I've been talking about in this lecture. Right? Yeah. The coupling, I mean, let me give you an example. The atoms have got a moment about 1 Bohr magnet. And if I put two magnetic moments, 1 Bohr magnet on, and I put them, say, 0.2 of a nanometer apart, that's the distance between two atoms. Right? The B field that one creates with the other, it's about 1 Tesla. Okay? Right? Now the energy of minus m dot b, right? The energy of 1 Bohr magneton in a field of 1 Tesla is 0.6 degrees Kelvin. So, but Curie temperatures might be 100 times as big. But the magnetic dipole fields in the solid, if it's a cubic solid, actually they all cancel out. If it's a tetragonal or hexagonal solid, they're only of this order of magnitude, about 1 Tesla. So they cannot possibly be responsible for magnetic order. The reason for magnetic order is it's not magnetic interactions that do it, it's Coulomb interactions, it's electrostatic interactions, coupled with the symmetry constraints of quantum mechanics. So that's why the magnetism of iron was a huge puzzle 100 years ago. Not just for the reason I said, was the Ampere's idea tells you that there's some huge surface current and you don't know why it doesn't melt, but also because the fields that you need in simple molecular field theory to explain the magnetism of iron, there has to be an internal field of 1,000 Tesla, simply to get 800 degrees or whatever the Curie temperature is. But Maxwell's equation says that D is continuous at the interface, so if you've got 1,000 Tesla inside, you must measure it outside, and you never do. So you need quantum mechanics to understand magnetism. And the fundamental interaction is a Coulomb interaction, which is responsible for magnetic order.
How permanent magnets are made?
Sorry?
How the permanent magnets?
Yeah, how are they made? Ah, yes. Well, yeah, they're made by sophisticated processes of metallurgy. Right? And you can say that between the day that someone discovers a new magnet in the lab, and that magnet is being optimized on the market, usually takes about 25 years. And it takes 25 years of hard work of a lot of people, usually in Japan, to get this done. Because it's not just the material that's important, but also the microstructure. And this, now, what you must understand is that any permanent magnet is in a metastable state. It doesn't want to be a permanent magnet. It wants to be a multi-domain magnet, right? Because the multi-domain state, it doesn't have to produce any field in space, right? And there's an energy associated with the field, right? It's a half mu naught h squared. Right? So it would much rather produce no field, and the way it can produce no field is to break up into domains. And it only has to pay a small penalty. It has to make domain rules. And so whenever you're trying to make a permanent magnet, you are fighting to maintain a thermodynamically metastable state of that material. And so you have to understand a lot about metallurgy and a lot about domain wall processes, and how particularly to pin domain walls or to stop reverse domains from nucleating in order to be able to end up with the microstructure you need for a good magnet. And as I say, that's been done exquisitely successfully for needle iron ore in Japan. And if you look at the microstructure of these optimized magnets, it's quite extraordinary what you see. I mean, there's always more than one phase, and the grain boundary phase may be only a few nanometers thick. Any other questions? Okay, well, probably next time I think I talk about materials, but then at that point I'll have had a chance to, I'll have a chance to look at your, I'll have a chance to look at your preferences, and later on we can try to tailor it to meet your choices.